Welcome to our lesson on expected value. Here's our one lone objective for this. We want to be able to calculate expected value of an event. Okay, we've already figured out how to calculate basic probabilities. Now we're going to use those probabilities to be able to predict the average amount that we get from a specific outcome that has numerical values associated with it. So these are normally used to figure out the expected value of games of chance, like buying lottery tickets or playing poker or roulette or things like that, or insurance policies. Things that have monetary values are what we normally use to calculate expected values. But basically, it works with any kind of situation where each outcome, right, each way that the experiment can happen results in a numerical value. So you couldn't do the expected value of flipping a coin because those outcomes are heads and tails. But you could do the expected value of rolling a six-sided die because those outcomes are the numbers 1 through 6 and they each have a probability associated with them, and we could very quickly and very easily calculate the expected value of that because as we see from the formula, it's very simply just the value of each outcome times its probability, and then you add them all up. So for the dice example, the values would just be the number, right, that you would see when you roll the die, and then the probability of each of those is of course 1/6, right? They're all 1/6. We're assuming that it's an equally weighted die and it's not some cheater kind of die. So all you have to do is multiply each of these together and add them, right? So you have 1/6 and then 2/6 and then 3/6, all the way down to 6/6, of course it's just 1. And you would add those all together, and that's going to be your expected value. Well, you can see that you're basically just going to have 1 plus 2 plus 3 plus 4 plus 5 plus 6 all added together, all divided by 6, right? Because you have 1/2 plus, or so 1/6 plus 2/6, right? 3, 4, 5, and 6. Those are all divided by 6. And when you add these together, this is 7, 7, and 7, right? 1, 2, 3 sevens. 7 times 3 is 21. You get 21 divided by 6. Of course, this becomes 7/2, which is 3.5. And it makes sense because they're all evenly weighted, so you should be basically right in the middle. You basically just took an average of all those numbers, and you can see that the average lands you right here in the middle of 3.5. So every time you roll a die, if you recorded the number on it and you did that a bunch of times and then you averaged all of those outcomes, it should average out to 3.5. Now, of course, it doesn't. In small experiments, remember we're talking about experimental probability versus theoretical, and this is in the theory, right? You could roll a die 3 times and get 3 6s in a row, and that obviously doesn't average 3.5. Or you could get 3 1s in a row, right? So it has to be a large amount before these things actually approach the theoretical. All right, see if you can use that technique to answer this question. Go ahead and pause the video and give it a try. Okay, did you get the right answer? 5.4. Okay, so the math is pretty easy when we're calculating expected values. Remember, it's just the value of the outcome times its probability, and then add all those together. And because of that, it's very easy to see and prove that the expected value of the sum of two events is equal to the sum of the individual expected values. So what this means is, think of it as like rolling a 6-sided die plus rolling, let's say, a 10-sided die, just so they're different, so like 2 6-sided die. So you roll a 6 and roll a 10-sided die. So now you're basically finding the expected value of those two dice, right, being rolled together would be exactly the same as the expected value of the 6-sided die plus the expected value of the 10-sided die. Okay? All right, how about another example? So the dining services on some university campus has observed that there are certain probabilities of students buying certain types of meal plans. And then the university expects a total enrollment of 8,421 students in the coming year. And based on that, they want to figure out some expected value questions. So here's the data. right? Based on previous year's data, that plan one, which consists of this stuff and costs this, 1 out of 10 students take that plan. That's what a probability of 1/10 means. And then 1 out of 15 chooses this one out of 30 chooses this one out of 10 chooses this one out of 12 chooses this one. And then, of course, there are going to be a certain number of students who don't choose any meal plan whatsoever. So if you change these all to a common denominator of 60, add them all together, you get 23/60ths. Right? These all add up to a little less than half. And if you do 1 minus that to figure out what's left over, that gives you 37/60ths. That's the probability of a student not getting a meal plan at all, right? A little bit more than half of the students don't buy a meal plan at all. Maybe they live at home, they're commuter students, maybe they live off campus, whatever, but there's the probability based on previous year's data. So now, based on that information, we can answer a few questions. Suppose we choose a student at random. What's the expected value for the amount that that student has spent on their meal plan? And basically what A is asking, it's really just asking what's the average amount of money per student paid for meal plans? Because that's really what an expected value is. It's an average, right? We added a bunch of stuff together. And you go, okay, but we didn't divide by anything. But we did, remember? Remember my simple example with the dice, right? Each one was technically being multiplied by its probability, but remember, a probability is always a fraction, which means it's always something divided by a number, right? And so when you're multiplying by a fraction, you're really dividing by something. And even though the probabilities are all different, right? In this case, they're all different, you can always put them over a common denominator, which now means all of these probabilities are being divided by the same thing. So when you think about it, in sense of probability, when we say 1 out of 10 being the same as 6 out of 60, that means that out of 60 total students, 5 of them were in this category, 6 in this, 2 in this, 4 in this, 6 in this, and then 37 of them in the category of no meal plan. So if you wanted to figure out the average number of things, you're just going to be dividing by 60 because that's how many total students we had, right? And so now if you want to figure out, well, how much money are they spent on average, don't you have to add up the total amount of money that the students spent and then divide by those 60 students, right? Because remember that we've now put it into over 60, so we're pretending like there are 60 students total. Well, then that means this amount of money is going to get multiplied by 6 because 6 students bought that plan. And this amount of money is going to get multiplied by 4. And this amount of money is going to get multiplied by 2. And this amount by 6. This amount by 5. And then, of course, this amount is 0. 0 times 37. And that would be how much total money they all spent. And then we would divide that total by 60, and that would give us the average amount of money per student, right? Well, think about the math. When I take 1245 and then multiply it by 6, and then this one times 4, blah, 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 and add those all together and divide by 60, isn't that the same thing as just taking each one of these and multiplying them by 6 and then dividing by 60, multiplying by 4 and then dividing by 60, right? So when you're multiplying by those fractions, and you think about it as one big old fraction, it becomes each number multiplied by its probability, added together and divided by how many things they are. You just did an average, right? So expected value is just an average. That's all it is. It's a mathematical average. It's a weighted mean is what we call it, because instead of just adding together these numbers, right? Instead of just taking the average of these numbers, we have to weight them by how many of each thing we have, right? We didn't have an equal number of each of those meal plans, so we can't just add those 5 numbers together and divide by 5. Or, if you think about it, add a 0 down here and add those together and divide by 6, because there's technically 6 options. We can't do that because each of those 6 options aren't equally weighted. We don't have the same number of students in each category. So we have to multiply each of these numbers by their weights. And then that gives us what's called a weighted mean. So an expected value is just a weighted mean. That's all it is. It's the average amount of money that a student pays for a meal plan. And then for part B, we can kind of do the same thing. Instead of looking at the cost of each meal plan, we can just look at the profit of each meal plan, right? Plan 1 makes $550, plan 2 makes this, and so on and so forth. Plan 1 is $510, plan 2 is $550, and so on and so forth. And of course, plan 6 is not buying any plan at all, so that has a profit of 0. And then we could do the same thing with the profits instead of the prices multiplied by their weights, and that's going to give us the average, right? The average profit. That's what the expected profit per student means. It's the average amount of money each student is going to pay for these meal plans. And then, of course, the overall profit, just take that average and multiply it by how many students we have. Okay, so these are basically just fancy old averages. Okay, so part A, we're talking about here that there is that zero component that we already talked about, the zero being the people who didn't get any meal plan at all. And that's what we have down here at the end is the 37 over 60 times zero. So you can see we've taken each probability times the cost of the meal plan, add those all together, and we get 403. So what does 403 mean? It means that on average, every single student pays $403 for their meal plan. And you might be thinking, well, that's not possible. You're right, it isn't possible. None of the meal plans cost $403. But it's because of there's so many students that didn't buy a meal plan that the average per student ends up being $403. It's the same idea that when we did the average, right, the expected value of rolling a six-sided die, we got 3.5, which is impossible. You can't roll a 3.5, right? You can roll a 3, you can roll a 5, but you can't roll a 3.5. That's because it's an average. It's not telling you that every single roll comes out to 3.5. It tells you that on average, you get 3.5. Just like no student paid 403, but on average, each student paid 403. Okay, if we do the same thing with the profits, right? Instead of costs, we just put in profits, which means the only thing that changes in this formula from before is these numbers change to profits instead of costs. This one's still zero, of course. And now we get 152.27, which means on average, they make a profit of $152.27 per student. Remember, that's per student, not just per student who buys a meal plan, but per every single student, because we're accounting for the 37 over 60, a little bit more than half of the students who don't buy any meal plan at all. So if we take that 152.27, multiply it by the number of projected students for the year, that says that the school, the dining services, can expect to make almost $1.3 million in profit for the year off of meal plans. Okay, a second example, roulette wheel. Same principle, right? We still have probabilities of outcomes, so we can still, and those outcomes have numbers, right? In this case, the number that you see on the wheel. So we can still calculate expected probabilities, expected winnings. So what's the probability of a roulette ball landing on a red pocket, or black for that matter, because they're the same? And by the way, if you don't know what a roulette wheel looks like, you can't really see this picture very good, but you get the numbers 1 through 36, and those alternate back and forth between black and red. And then you get two green zeros, a 0 and a double 0 are they do that just so that they have the winning advantage, right? Because now we can calculate the probability that the ball lands on red and the probability that it doesn't land on red, and then we can figure out the expected value for play in this game. All right, so the probability that it lands on red is the 18, because if you have the numbers 1 through 36, half of them are red and half of them are black, so you take half of 36, that gives you 18. So you get 18 good over the total of 38, because that's the 36 plus the two greens, right? So the probability of landing on a red is 18 over 38, which of course would reduce, right? We'd put 9 over 39, but we're just leaving it as 38 to remind ourselves these numbers are coming from the total number of things on the wheel. Okay, so if that's the case, if 18 over 38 is the probability of red, then obviously the probability of not red is 1 minus that, and that's the other 20 spots on the wheel, the 20 over 38, right? So we can very easily figure out the expected value of playing this game. If you plop down $1 and bet on red, or really on black, doesn't matter because the odds are the same, right? Probabilities are the same. Then you win, right? So you get $1 if you win, and there's the probability of winning, plus you lose your dollar, minus 1, and there's your probability of losing. And when you do all the math, right, you get negative 2/38, which is roughly 5 cents. So what does this mean? Well, this means that on average, if you were to play this game over and over and over and over and over again and just keep betting black every single time, or kept betting red every single time, you played that same typical kind of bet, then in the long run, you are expected to lose 5 cents every time you play the game. And again, that's impossible, right? You either win $1 or lose $1, but on average, it averages out. Sometimes you win, sometimes you lose, but it averages out that you lose more than you win, just a little bit more, but that little bit more is enough that you lose on average 5 cents every time you play the game. It's really not exactly 5 cents. As you can see, it's 0.0526. So if you played the game 10 times, you would expect to lose 53 cents per average. If you played it 1,000 times, you'd expect to lose about $52.60 on average over 1,000 spins of the wheel. And you go, okay, well, big deal, 52 bucks. How is Vegas making money? Well, because take that $52 and now multiply it by the millions of people that are playing this game every single day, and you can see that very quickly they're making millions and millions of dollars every single day. That's how it works. Now, if you want one last kind of little brain exercise, I've got two of them for you. This one is there's a difference between the American roulette wheel and the European roulette wheel. The European roulette wheel only has one green spot, right? It's a green zero instead of that also having the green double zero. So that means their odds, right, are very much closer to 1-to-1. Their probabilities are very a lot closer to a half, right? 0.5 and 0.5 because you only have one extra spot. So it's going to be, instead of 18 over 38, it's going to be 18 over 37. And I know that doesn't seem like a lot, but it does actually change things. And so you could calculate your expected value on that machine. It's still going to be negative, right? Because they still got to make money. Okay, and then our last skill check is because we're dealing with probabilities, we need to make sure that we can actually convert from odds to probabilities. So if I give you the odds on a bet are 4-to-1 against, what is the probability of winning that bet? Pause it, make sure you... All right, did you remember that when you do odds, right, probability just becomes good over total. These represent the two pieces of the total, so 4 plus 1 is 5, and the reason why it's 1 over 5 and not 4 over 5 is because these are the odds against, so the probability of winning, which would be the probability of it happening, is now the 1 over the total, 1/5 or 20%. All right, that's everything we need to know for expected value.